Hello, Mr. Fig back here. This week we're going to be discussing how waves reflect and create images in mirrors. For now, we're going to start with plane mirrors or flat mirrors, the kind you might look at in the morning when you're brushing your teeth or when you're getting dressed to go out. Last week you'll remember that we introduced the concept of a ray, that a ray is an arrow, a vector that we draw to describe how the wavefronts are moving from a wave. So these rays are incredibly important if I want to determine how an image is forming. So here I have two rays shown. The incident ray here coming in represents the incoming wave, and it strikes this mirror, and then this red arrow represents the reflected ray. This black dotted line here down the middle is called a normal, and we draw that for a reference. It's a very important reference line. The word normal comes from geometry. It simply means a line perpendicular to a surface. Well, the law of reflection simply states that the angle of the incident ray will always be equal to the angle of the reflected ray when measured from a normal line, this black dot perpendicular. Well, it's a very simple rule. But before we go any more with it, I want to remind ourselves that these rays are not really what a wave is. These rays just show me how the wave is moving. In reality, the wave is a series of wavefronts carrying energy. So we should, in the back of our mind, be thinking of reflection more like this. I have wavefronts of the incoming wave moving in, striking the mirror, and then reflecting back out. That's really what's going on. But drawing all those wavefronts will make a pretty confusing diagram. It's much easier to draw these rays and to work with those. In fact, this angle of the incident ray equal to the angle of the refraction ray, it's very simple mathematically. It just means that theta I equals theta R, where theta I is the angle of the incoming light measured from the perpendicular normal, and theta R is the angle of the outgoing light as measured from the perpendicular normal again. All right, so I'd like to take a moment. We'll take a look at a little bit more about these wavefronts, moving wavefronts, and what these rays represent. And then we'll come back and discuss mirrors a little bit more. So what we're looking at here is a representation of a physics device called a ripple tank. Now, a ripple tank is simply a shallow tank of water where you could create water waves in them, and then using a strobe light, examine the motion of those waves. I have nothing as complicated as a ripple tank here at home, so this simulation will have to do. But what you see at the top here, this represents a plane wave, that's P-L-A-N-E, of straight wave moving down from the top of the tank. The bright spot here represents the wave peak, or the wave front, as that we'll see in motion. The dark spots represents the trough of the wave. And this yellow line that I've placed diagonally across the tank represents a wall. It's a barrier. And what I'd like to do is watch what happens when this incident wave comes down from the top of the tank and strikes this barrier. So let me put the waves into motion and we can take a look at what happens. So the waves are about to interact with that barrier, and as the wave strikes the barrier, you'll see that a reflected wave forms going off to the right. It's going off to the right because I purposely chose 45 degrees when I set up this barrier. Now let me stop the motion so we get a little bit of better view. So we can actually see that the view of the wavefronts is fairly complicated. I have the incident wavefronts coming down, and then this reflected wave, and then I get this checkerboard pattern because the waves are actually interfering with each other. The bright spots represent where the waves are constructively interfering, and the dark spots where the waves are canceling out. They're destructively interfering because they're out of phase. So I usually don't look at reflection in terms of wavefronts. We'd like to simplify our view by describing the motion of the incident wave and the reflected wave using a ray. And remember, a ray is simply a vector that I draw perpendicular to the wave to show how the wave is moving. So let me try to mark that. So here I have my incident wave coming down, and it strikes the barrier right here. Now it actually strikes the barrier all across. I'm just choosing one location to look at. I'm looking at the part of the wave that strikes right there. And this ray represents my incident wave, the wave coming from the top. Now, I'm going to draw another ray representing the reflected ray. My reflected ray is traveling that way as this wave bounces off the wall. Now, the law of reflection says that the angle of these two rays should be equal, but only when measured from a particular reference line. And that reference line is a normal line drawn perpendicular to the surface where this incident wave hits. Well, this incident ray hits right here. So let me draw my reference line in. And again, this is known as a normal line. The word normal in math simply means a line drawn perpendicular to a surface, and that's what this is right here. It's the same use of the term when we talked about a normal force when we dealt with forces. Now, my drawing skills aside, you can see that the angle here, this is the angle of incidence. And it is, in fact, about the same as here, this angle of reflection. So when we say that the angle of incidence and the angle of reflection are the same, it's only when we are actually measuring to this perpendicular normal line. So you'll see that it's much easier to draw the motion of the waves with these vectors than it is the wave fronts. But it's important to remember that it's the wave fronts that is actually the energy and the real physics part of the wave that's actually happening. Just mathematically, it's a lot easier for us to deal with vectors than it is by drawing the whole wave. Okay, back to the presentation. Well, back to talking about mirrors. A smooth surface is needed for reflected rays to create a clear image. Here you have a picture of two surfaces. On the left here, picture A, the surface is a little bit rough. So the incoming light, as it comes in, is going to reflect in different angles. This is going to produce a diffuse reflection. You're not going to see a clear image. There might be a hazy image, but it's not going to be clear. I need a smooth surface, so as the light strikes the mirror and bounces out, the rays stay spaced out exactly the same way as they came in. This is known as specular reflection, and it results in a clear image. A plain mirror that you use at your house, where you can clearly see yourself in the mirror, creates an image due to the fact that it's smooth and it produces specular reflection. So, if we take a look here at this kitten in the mirror, it's a familiar sight to us. We often we know that our image will look the same as we do on the outside behind the mirror. But why is that? So let's take a look and construct a ray diagram to see how the image in a flat mirror is actually produced. Here I have a cat sitting in front of a mirror. This gray line in the middle here represents the mirror. So how does a reflection create an image in the mirror? Well, first I have to realize that if I am seeing an object, it means that light is bouncing off that object and into my eye. So consider, say, the ear of this cat. If I can see that, it means that light is bouncing off the ear, and some of that light will bounce in my eye. Some of this light will actually bounce in towards the mirror, but light is bouncing in all directions. If I'm standing back here, I'd see the cat. If I'm standing over here by the mirror, I'd see the cat. So all this light is being reflected from that one point of the cat. But I could say the same thing for every point of the cat is producing light reflecting in all different directions. So the light rays scatter off the cat's ear in all directions. Well, that's confusing, and luckily I don't really need to look at all directions. What I need to do is just take a look at those rays and pick two to work with. So I'm going to pick two incident rays and start with that. Alright, so here I've eliminated most of those rays coming off the cat's ear, and I'm just looking at two rays of light bouncing off the cat's ear, and I wanted to pick two rays that will actually strike the mirror because I'm looking to see where the image will form in the mirror. Well, if before I I need to draw the reflections, but before I draw the reflections, I need to draw those reference normal lines in. So I carefully draw the normal lines in, and then I want to draw the reflections, making sure that I keep those angles consistent. So there are my normal lines, and there are my reflections. Now notice that this reflection here, because the one of the rays I chose went straight to the mirror, that's along a normal line. So that technically has an angle of 0. So the reflection bounces off with an angle of 0 right back along itself. But this incident light, when I draw the normal line from where this ray of light strikes the mirror, it has a small angle. I need to be very careful and make sure I match the same angle above when I draw in my reflection. If I was doing this with a paper and a pencil, I would use a protractor to be exact. However, I'm doing this on a computer, and it's a lot easier for me to create a good angle with the computer drawing tools I'm using. Well, how does this tell me where the image of the cat is? Well, this light came from the cat ear. Where the image will be is where these two reflections cross. Now, the reflections don't cross on this side of the mirror. Since my reflections don't cross on this side of the mirror, I want to extend those reflections backwards to see where they would appear to cross. The light appears the two reflections appear to be crossing right back here. So since that light originally came from the cat's ear, I would see the cat's ear in that location. All right, well, what about the rest of the cat? Well, if I want to see the rest of the cat's image, I need to repeat the process for more points on the object, on the cat. Now, to be exact, I could do all the points of the cat, but once I do a couple of points, I can pretty much figure out what the image is going to look like. So let's take a look at the cat's tail next. So I want to repeat the process for the tail. So again, here's the tip of the tail. I'm going to need to pick 2 rays of light, and I can pick any 2 I want, but I want 2 to strike the mirror. And I'm going to need to add normal lines again so I can see my reflections. Well, this image is going to get pretty crowded, so let me remove some of the work we did before. So I'm removing the rays from the cat ear, and let's just look at the reflections from the tail. Again, I chose a ray that went straight along the normal line, so no angle of incidence, and so when the reflection will come back with no angle and bounce right back along itself. And again, I was careful measuring the angle here between this blue normal line and this green incoming light, and to make sure I get the reflection in the correct location. Well, again, these reflections don't cross on the side of the mirror, so I'm going to do the same trick. I'm going to project these reflections backwards to see where the reflections came from. The 2 reflections appear to be coming from this spot behind the mirror. Since that light again started at the tip of the tail, that's where I would see the tip of the cat's tail in the mirror. You can pretty much see what's happening here. If I duplicate every position of the cat, I will build up spot by spot of where the image is. So just repeat, and I would eventually see that the actual cat image looks like this. So a couple of things you can note. Note that the image is reversed. That's simply a result of how these rays reflect and projecting them backwards. But other than that, the cat seems to be about the same distance behind the mirror as it is in front of the mirror. An effect that we're very much used to looking at mirrors in our own house. So some important definitions of what we say. We say that the image from a plane mirror is virtual, upright, reversed, and the same height as the object. That's a lot of vocab. Let's cover it a little bit at a time. First off, the easiest one is the height. The measured height of the object we label with HO for height of the object. The image on a flat mirror and a plane mirror always appears to have the same height as my object. So the height of the image, same as the height of the object. The object distance is the distance from the object from the center of the mirror. So we usually use the letter P traditionally to represent the object distance. It seems a little odd, but I'll explain it in a minute. The image distance is how far behind the mirror the image appears to be. Now, we can't really go behind a mirror, so there's no way to measure the image distance, but it appears always to be the same distance behind the mirror as in front of the mirror. We call the image distance Q. The reason why they choose P and Q is P and Q kind of looks like reflections of each other. So P is the real is the object, Q represents the image. I always remember it this way. You have an object before an image, and you have the letter P before Q in the alphabet. So P for object, Q for image. Now, what do we mean about real and virtual? Well, in optics, which we're studying, real represents light that I can physically touch. This cat is in the real world, so the light that's bouncing off the cat I can actually touch and feel, and it can bounce into my eyes directly, and so that we call real. And so I say the object is real, it's on the real side where the light is, I can touch the light, and I say that this object distance is real because it's on the side of the mirror where I can touch the light. But I can't touch what's behind a mirror. There's nothing really there. So we call what's behind the mirror virtual. This is a virtual image because I can't physically actually touch it. It's where the image seems to be based on projecting those reflections backwards. But I can't put my hand through the mirror and see the cat there. I can't look behind the mirror and see the cat there. We'll later learn that a real image can be projected, shined onto a piece of paper, where a virtual image cannot. There's no way to take a flat mirror and get the image to show up on a screen of some type. We say that the object is real. We say that this image is virtual. And there you go. So just by a very simple rule, the angle of an incident light always reflects at the same angle when measured from that normal line, allows us to construct the image we see in a plane mirror. Not everything, of course, is flat. I wonder what happens if the mirror is curved. Before the next video, grab a shiny spoon out of your kitchen drawer and look at both sides, carefully at both sides, and see if you can see an image of yourself in the spoon. And you'll notice a very different image depending on which side you look at. Something we'll discuss next time. But I'd like to do a practice problem based on this. So let's take a look at one. So here's a flat mirror with a bunch of mice in front of it. And this floating, disembodied eye represents your point of view. And I would like to know which mice I can see in this mirror. So when you look at a mirror, the image you see in the mirror depends on how far away from the mirror you are and your position relative to the mirror. So in order to determine what you can see in the mirror, the first thing you want to do is draw the reflected light from the edges of the mirror that have to bounce to your eye. So these two red vectors represents reflected light from the mirror going to my eye. Well, where did that light come from? Well, in order to figure that out, I have to add normal lines to where the light was bounced off the mirror, just like we did in the previous example. So let's add some normal lines. So I've added two normal lines. Now, I would like to see where this light originally came from. Remember, this light is going from the mirror to my eye. That's why the arrows points to my eye. But let's take, for example, this ray. Well, this is the angle of reflection. The angle of incidence would be below this blue line, the blue normal, and so the incoming light should be coming from this way. Now, this light has a large angle of reflection, and again, I would have to make an equally large angle of incidence below. So let's draw the incident rays. So here, this green ray represents light coming in, and then it hit the mirror and it bounced into my eye. Here, this green ray hit the edge of the mirror and then bounced into my eyes. Now, these are the two extreme incident rays. Anything between these two incident rays, I'll see in the mirror. Anything outside these two rays, I won't see in the mirror. So I can see D, B, E, H, and G are all being seen in the mirror. But A, F, and C are not in the mirror. They would not be reflected. And there you go. Just a little bit of geometry and very little math to a plane mirror. Okay, well, next time we'll take a look at curved mirrors and apply the same rules and get some very different results. See you next time.